So in this Fourier series, we lay down the basis of Fourier series as well as the Fourier transform, and then the complex form of Fourier series, obviously. Now, the applicability of this Fourier series is too much, and that's why every engineer has to study this, whether he is from any domain. Okay, and that's why we are in Fourier series today. Okay, now what is the Fourier series, or why it exists, how it exists? Okay, how it looks like. Okay, or why the particular functions were chosen. Okay, so Fourier series is also called as the trigonometric series. Now, the question is, if we have already the series expansions, we have studied the Taylor series expansion as well as we have studied the Maclaurin series expansion. Okay, so if I know the Fourier, Taylor series expansion, if I know the Maclaurin series expansion, what is the need, or why this Fourier series is so important, or why we have to go or shift from Taylor series expansion to the Fourier series expansion? The question is, or the answer is, see, when we think of the Taylor series, or when we think of the Maclaurin series, we need a function to be infinitely differentiable. Yeah. So that is the trouble. So need not necessary that our function is going to be infinitely differentiable every time. So for example, if I consider f of x, okay, so f of x or x square I consider, okay, then x square I will have the first derivative 2x, the second derivative will be 2, and what about the third derivative? 0. Okay, so that means I cannot have more than 2 derivatives for this function. Then how I am able to get the Taylor series for this, or how I am able to get the Maclaurin series for this? And that's why I cannot have the component-wise analysis of this signal. Okay, so for mathematicians it is a function, for the engineers it is going to be a signal. Okay, and hence we don't have the Taylor series expansion for this signal, or we cannot have the component-wise analysis for this signal. So when I say the component-wise analysis, that means I am going to find the different frequencies present in this signal. Okay, so whether it is a time signal or whether it is going to be a frequency signal, so I am going to analyze it component-wise. What are the components of this signal? Okay, and hence the Taylor series or Maclaurin series has the limitation that it is existing if and only if the function is infinitely differentiable. Okay, so then we are in trouble. Correct. Okay, and hence we have to go for the Fourier series. So Fourier series is also called as trigonometric series. Okay, or we called it as trigonometric series. Why we call it as trigonometric series? Because we represent every function. Okay, I repeat, every function using the sine and cosine functions. Okay, so we consider the set of sine functions and set of cosine functions, and then we can represent every function using this. Okay, and that's why this is called as the trigonometric series also. Okay, now the question is Fourier series exist for every can we find the Fourier series for every function? Okay, so answer is we have to be careful. Yes. So when a function satisfies Dirichlet's conditions, okay, so this is very important. When the function satisfies Dirichlet's conditions, then and then only we are able to find out the Fourier series of that function. Okay, so yes, there is a condition for the existence, and that condition is called the Dirichlet's condition. So if that is satisfied, we are done. Okay, and now let us see the Fourier series in detail. So we'll see the formulas, and then we'll see how and it is dependent on the interval as the function also. So let's go to the formulas now. I hope you are able to see my screen.
Yes, sir.
Oh, that's great. Good. Okay, so let's see the Fourier series expansion. Okay, now as I said, the function should be defined in the interval. So let's have let f of x be defined in. So be careful that x is going to be a general variable for us. So that's why I am writing this x. You can have any variable and you can analyze or apply this Fourier series in any domain. Okay, so that's why I'm taking the general variable f of x defined in the interval c to c plus 2l. So this is the general interval c to c plus 2l, where the length of this interval is going to be 2l. Okay, satisfying Dirichlet's conditions. Dirichlet is a mathematician, so who laid down the condition for existence of Fourier series. So he has given the conditions for existence of Fourier series. Okay, then the Fourier series expansion of f of x is given as. Okay, so we have f of x is equal to a0 plus summation an cos of n pi x by l plus summation n running from 1 to infinity bn sine of n pi x by l. Okay, so here we have to be careful that summation is always running over n, from n is going to be 1 to infinity, where this an, bn and a0 are the constants to be determined. So how we determine these coefficients? So where a0 is equal to 1 upon 2l integral c to c plus 2l. Okay, c to c plus 2l f of x dx. Then an is equal to 1 upon l integral c to c plus 2l f of x cos of n pi x by l dx. And we determine bn as 1 upon l integral c to c plus 2l f of x sine of n pi x by l dx. Okay, so this is how the Fourier series is defined, and this is how we are able to calculate the coefficients in this Fourier series. Okay, so as I told you, this Fourier series can store the infinitely many data. Okay, so for example, you have to store the data of the employees. Okay, then what you can do is you can assign this A0 as the employee number. You can assign this coefficients ANs as the professional data of that employee. So for example, what is his post? Okay, then when he joined the organization, then when is his superannuation, when is his increment, when what is the experience he has, and all this. And this coefficients b, and so you can assign the data like personal data. So what was his height when he joined, what was his weight when he joined, and so many biometric features of that particular person. And so this gives you a unique way to represent the data of infinitely many data as well as for infinitely many employees. So that's why this is very useful in storing the data also. Okay. Now, when we say this function satisfy Dirichlet's condition. So what are the Dirichlet's condition? So first, the function is a single valued function, which is a integrable function, differentiable function, and it has the finite number of maxima minima. So in other words, it is the bounded one. Okay. So when we say it has a finite number of maxima minima, that means it is bounded in the interval c to c plus 2l. And if this Dirichlet's conditions are satisfied, then we say the function has the Fourier series expansion, and we are able to find the Fourier series expansion using this formula. Okay, so again, there is one more relation which we have to understand apart from the Fourier series. So once you know the Fourier series exists for any function, okay, then we have the another concept associated with that is the Parseval's identity. Okay, so we need to understand what is going to be the Parseval's identity. So we have here Parseval's identity. Okay, so Parseval's identity relates the coefficient in the Fourier series as, okay, so we have the 1 upon 2l integral c to c plus 2l f of x bracket square dx is equal to a0 square plus half of summation n running from 1 to infinity. You have an square plus bn square. Okay, so this Parseval's identity gives us the foundation to prove the claim, or it relates the coefficients in the Fourier series expansion. So this is same as a0, an, and bn that we have taken from the Fourier series expansion of the function. And this identity helps us to prove the claim, or to prove the another identities which are very important, like Riemannian zeta function can be proved using this Parseval's identity. There are so many claims by Ramanujan, the great mathematician, and that can be proved by this Parseval's identity also. So before uh, it was known to the Ramanujan that these identities exist, and later on this were proved using this Fourier series expansion, and some identities are proved using the Parseval's identity. Okay, so remember that this is the master formula. So your entire chapter is along this two formulas. Okay, so this is the master formula. Any formula in this chapter can be derived from these two identities. This is the master formula is c to c plus 2l is any interval. You can find the Fourier series expansion, and then if required, you can prove the claim using the Parseval's identity. Okay, and now what we have to study particularly how that intervals are obtained from this interval that I'm going to do now. Okay, so I'm going to obtain everything from this formula. So this is the master formula for this chapter. Entire chapter depends on this one formula. And now we'll be studying the different cases for this formula. So I'll go with one by one. Okay, so first I'll have, okay, let c is equal to 0 and l is equal to pi. Okay, so that what is the interval c to c plus 2l will become, see, c is going to be 0, so this will be 0, and c plus 2l, so it will going to be 0 plus 2 pi. So this interval will become 0 to 2 pi. Okay, and now once I have this 0 to 2 pi, now I have to see that how I'll get, or what I'll get as the Fourier series expansion exactly. Okay, so let us see how this formulas will change in the interval 0 to 2 pi. Okay, so here we have f of x is equal to a0 plus summation n running from 1 to infinity, and we'll be having an cos of nx plus summation n running from 1 to infinity, and we have bn sine of nx. So this is equation 1. This is the Fourier series that we will be getting, and where I'll have a0 is equal to 1 upon 2 pi 0 to 2 pi f of x dx. An is equal to 1 upon pi 0 to 2 pi f of x into cos of nx dx. Okay. And we have bn is equal to, okay, so what will get bn? 1 upon pi integral 0 to 2 pi f of x. Yeah, so we have here f of x into sine of n pi x. I'm sorry, you will get here L is going to be pi, so it will get cancelled. So you will be having directly the nx here, nx and dx. Okay, so see this formula. Okay, this is the master formula that we have, and we put this L is equal to pi, so this pi will get cancelled, and then c is going to be 0, so integral will be 0 to 2 pi, and this will be 1 upon 2 pi. So according to that, we have changed the formulas here, and we got this. Okay, so if I change the c to 0 and L to pi, then I'll get this interval. Now the second one, what I'll do is I'll put c is equal to minus pi, and I'll keep L is equal to pi as it is. So what will happen to the interval c to c plus 2L? This interval will become minus pi. Now c is going to be minus pi to pi. Okay, you can write this. This will be minus pi plus 2 pi, and so you'll get pi. Okay, and once you have this interval c to uh, 2L as minus pi to pi, then we are able to write the Fourier series. So what we'll get here, we have the Fourier series f of x has a0 plus summation n running from 1 to infinity. Then you have an cos of nx plus we have summation n running from 1 to infinity, and then we have bn, and here sine of nx. So this is equation 1, where we will be having a0. So please be careful while writing the formulas. Now the interval is minus pi to pi, and you'll be having f of x dx. Then we have an is equal to 1 upon pi integral minus pi to pi f of x into cos of nx dx, and we get here dn is equal to 1 upon pi integral minus pi to pi f of x and sine of nx dx. Okay, so we can see we are able to write this formulas in the interval minus pi to pi. Okay, and then accordingly the Parseval's identity will go on changing in each interval. So if I want to think of the Parseval's identity, what will happen to the Parseval's identity? Only the limits here will go on changing, because as we are finding a0, a and bn in the Fourier series. So after finding the Fourier series only you can use the Parseval's identity. You cannot use the Parseval's identity directly. Okay, so we have to be careful. And now we go with the next. So what we did here, we put c is equal to 0. We put c is equal to minus pi, and let what happens if I put only c is equal to 0. So I do not change the L. So the interval c to c plus 2L will now become 0 to 2L. because I am putting 0, I am not replacing L here, and hence I get this. So what will happen now for this? Okay, then I can have that, or we have the Fourier series f of x is equal to a0, and I'll be having plus summation n running from 1 to infinity. Then we got an cos of n pi x by L plus summation n running from 1 to infinity bn sine of n pi x by L. This is equation 1, where a0 is equal to 1 upon 2L integral 0 to 2L f of x dx. An is equal to 1 upon L 0 to 2L f of x cos of n pi x by L dx, and we have Bn is equal to 1 upon L integral 0 to 2L f of x sine of n pi x by L dx. Okay, so this way we are able to get the formula for the interval 0 to 2L. Okay, and then now what will happen the next? Okay, so this is the third one. All right. Now, if I put C is equal to minus L. Okay, so suppose C goes minus L. So I'll assume that let C is equal to minus L, and hence the interval C to C plus 2L will become minus L to L. Okay, so what will be the changes in this interval C equal to minus L? So the interval is minus L to L. Then we have, what will be having the case, f of x is equal to a0 plus summation n running from 1 to infinity an cos of n pi x by L plus summation n running from 1 to infinity bn sine of n pi x by L. So this is going to be equation 1, and where a0 is equal to 1 upon 2L minus L to L f of x dx. An is equal to 1 upon L minus L to L f of cos of n pi x by L dx, and Bn is equal to 1 upon L minus L to L f of x sine of n pi x by L and dx. Okay, so this is how we are able to get the different cases from the master formula itself. So you can see I have derived everything from the same formula which I have written at the first C to C plus 2L. So if you can understand this master formula for the interval C to C plus 2L, then we are able to find the formula for any interval. Okay, so whatever the, so up to 8 we have seen only the interval. So I changed only the value of C and L, and so I was able to get the formulas for all the intervals. So to remember this better, we need to understand only the first formula, Okay, so which is a master formula for the interval c to c plus 2l, and then just change the value. So whenever you have given any interval, compare that interval to c to c plus 2l. Okay, and you will get the value of c, you will get the value of l, and so you can put the value of c and value of l in the formula, and you can generate the formula for any interval. Okay, and that's what I said. The first formula is the master formula to derive any all of this. Okay, so up to 8 we have seen the formula is based on the interval. Okay, now what if I know some additional information about the function? Okay, so first is the interval, next is the function. So let us see what will happen to the function if I know some additional property, and which additional property I have to know for this. Okay, so the basic thing that we have seen earlier in class 11 or 12. Okay, so the type of function that I want to think is whether it is even or odd function. So what or how I am able to define even function? Okay, so when I say the function is a even function, okay, so the function f of x defined in the interval minus a to a is said to be an even function if f of minus x is same as f of x. Okay, so we can have, for example, let f of x is equal to cos of x be defined in minus a to a. Then we need to check how whether this function is a even function or odd function. Okay, so we consider f of minus x. So what will be f of minus x? It will be cos of x will be replaced by minus x. And now what we know is cos of minus theta is same as cos of theta. And so we can have this is cos of x only, which is function of x. So if I know that f of minus x is equal to f of x, then the condition for even function is satisfied, and hence f of x is an even function. So this way we are able to identify and we are able to define the even function. So the important condition that we have to be careful. So what we get here, f of minus x is same as f of x, and when we have f of minus x is same as f of x, then we say the function is going to be even function. Now we have to think of the odd function. Okay, so what we have, the odd function. So here the function f of x defined in minus a to a is said to be an odd function if f of minus x is minus f of x. So we can consider, let f of x is equal to sin x be defined in minus a to a. Now let us check whether this function is an odd function or whether this function is an even function. Okay, so we have f of minus x is equal to sine of minus x. And what we know is sine of minus theta is minus sine of theta. So using this, I'm able to write minus sine of x, which is minus f of x. So what we get here, f of minus x is minus times f of x. Okay, and hence the condition of our function is satisfied. So we can say hence f of x is an odd function. Okay, so we got that if this condition is satisfied, then we say the function is odd function. But the most important condition that we need to understand is the function is defined in the interval minus L to L. So here also we have seen the function is defined in the interval minus A to A, and then we check this f of minus x is equal to f of x. So the first thing that we need to understand is where the function is defined. What is the interval of the function? And then we have to decide whether to check minus x or x, minus x for f of minus x. So when you have to check for the even and odd function, if you know the function is defined in the symmetric interval about 0. So this is also the symmetric interval about 0. So minus a to a is a symmetric interval about 0. So if your interval is symmetric about 0, that means it contains negative and positive parts of x-axis. Then only we have to check for the even and odd function. Now the next question is, what is the benefit of this even and odd function to us? Okay, so why we are checking the even and odd function? Okay, so now we can see the sine function is going to be an odd function and the cosine function is going to be an odd function. And if I know the sine and cosine are even and odd function, then you can see this is the series where we have to find out the integrals in terms of sine and cosine always. Okay, so in an we always need the cosine term, in bn we always need the sine term. And now the question is, if I know about the sine and cosine term, what will be the product or what will be the nature of this product? If I know this is going to be an odd function, and what happens to this function if I know about f of x, whether it is going to be odd and even, then what I will have for this product. So we have to consider what will be the product of two functions when we know that uh, both of them either it is going to be even or it is going to be odd. So we need to consider the product of functions. Okay, so what will be the nature of this product of these functions? Okay, so if I know, okay, so if I know the function f of x, if I know the function g of x, so f of x is there, g of x is there, then what will be the nature of this product f of x into g of x? So if I know that this f of x is either even function or it is going to be odd function, then g of x is even or odd, even or odd. Okay, then what will be the product of two even functions? It is going to be even function. The product of one even and one odd is going to be odd, and the product of two odd function is going to be even function. So this way we are able to find the product of any two functions if I know about that functions, whether they are going to be even or odd functions. Now, as I said, what will be the benefit of knowing the product or knowing this function? Okay, then the important thing that we have, okay, integral minus a to a. See that we are all checking for the functions in the interval or the symmetric interval minus a to a. Then I know about this integral. If I know about the function, whether it is a even function or whether it is an odd function, then the integral minus a to a f of x dx is equal to twice integral 0 to a f of x dx if I know that if f of x is an even function. So if I know that f of x is a even function, then directly I can convert this integral to twice integral 0 to a. And what if it is going to be an odd function? So if f of x is an odd function, so if it is an odd function, then the integral is going to be straightforward 0, and that's what the benefit is. Yeah. Okay. So if I know the function is going to be an even function, then I can convert this integral to twice 0 to a f of x dx. And if I know this function is going to be an odd function, then the integral is going to be 0 directly. Okay, and hence that is the use of knowing the function, the nature of the function. And now the question is, which are the intervals where we can apply this? Okay, so see, I want the interval to be symmetric, minus a to a. So what are the symmetric interval that we have seen up to yet? So can you tell me what are the symmetric intervals? So we have seen up to 1 to 4 formula. See, I will go from the interval again. So first interval is 0 to L. Second is going to be minus pi to pi. The third is going to be 0 to 2L. And the fourth interval is minus L to L. So these are the intervals we have seen. And now the question is, in which interval we can apply the even and odd function, or where this will be applicable. So we have seen the interval here 0 to 2 pi. Then we have seen minus pi to pi. Then we have seen 0 to 2L. And then we have seen minus L to L. So which are the intervals where we can see, or where we can apply this even odd theory? Minus to positive. Okay, so minimum to maximum. Okay, so that's why that's correct. Okay, so you got the point that the intervals where we have minus to plus, so that are the symmetric intervals. So here what I have is this interval and this interval, and I have this interval. So I can consider the this interval and apply the even odd theory. I can consider this interval and you apply the even odd theory. So when in the examination or in the problem given to you that minus pi to pi is the interval or minus L to L is the interval, then you have to think that is there additional property of the function where I can apply the even odd theory and then simplify my work. Okay, so the question is how you will get your work simplified, or how this theory reduces your work. Okay, so we go for the next formula, and here the additional information that either the function is even or the function is odd. Okay, so what I have here, let f of x be an even function, even function defined in minus pi to pi. Okay, so this is the additional information given to you that the function is even function, and we have this is the even function defining in the interval minus pi to pi. Then what we'll get here? Okay, so we have, okay, uh, one thing we know that if the function is even function, okay, so if the function is even function, then their product with the odd function is going to be odd. So what we have in the interval minus pi to pi. Okay, so let us see here. Yeah, this is minus pi to pi. So this function is going to be even function. These are the two even functions. So product is going to be even function. This is a even function and this is odd function. So product is going to be odd function. And we know the integral for odd function is going to be 0. So that means all bn's will be 0. Okay. So here what we'll get is, if I know the function is an even function, then I'll get all bn is equal to 0. So that is the important thing that we got. And hence we have here Bn is equal to 0. Okay, so for all n, this Bn is going to be 0. And if Bn is going to be 0, then the Fourier series expansion Fourier series expansion of f of x is given as. So what will be the Fourier series expansion? F of x is equal to a0 plus summation n going from 1 to infinity. Here you have, this is an, and here we'll have cos of nx. This is equation 1. Because we know bn is going to be 0, so next term we don't have to write. And now here we have to calculate only an and a0. So where a0 is equal to, please be careful for the formula. Then we'll be having integral 0 to pi f of x dx, and we have an is equal to 2 upon pi integral 0 to pi f of x cos of nx dx. Okay, so now the question is, how do we get this? Okay, so I'll show you how do we get this. So we have the formula for a0 is 1 upon 2 pi minus pi to pi f of x dx. This is the formula that we have. Now, this being a even function, so what I can have is 1 upon 2 pi. I can write this as twice integral 0 to pi f of x dx. So this 2 and this 2 will get cancelled, and you will be having this formula. So it is easy to have this formula. So this formula is again obtained by using the previous formulas. Okay, so this is how we are able to get the formula for a0 and an. And now what happens if I have this is going to be odd function. So let us see that the function is an odd function. So we can have the next formula. Let f of x be an odd function. Okay, odd function defined in minus pi to pi. Okay, so if it is defined in minus pi to pi, now this is going to be odd function. So what will happen to the a0 and an? That will be 0 now. So we have a0 is equal to an is equal to 0. Okay, so when the function is odd function, these two coefficients will be 0, and then the Fourier series expansion of f of x is given as. So what you have here, f of x is equal to a0 and an is going to be 0. So there will be only bn. So into summation 1 to infinity, then running from 1 to infinity bn, and here we have sine of nx. Let it equation 1, where we have bn is equal to 2 upon pi integral 0 to pi f of x, and we have sine of nx dx. So this is the benefit of knowing whether the function is an even function or is an odd function. And now this we have seen for the interval minus pi to pi. The same thing will happen with the interval minus L to L. So that we'll see. So let f of x be an even function defined defined in minus L to L. Okay, so we get here, we have again you'll be having bn is equal to 0, since it is going to be the even function, and we have the Fourier series of f of x as f of x is equal to a0 plus summation n running from 1 to infinity, and you will be having an here, an cos of, now see the interval. The interval is minus L to here, so this will be n pi x by L. This is equation 1, and then we get here where what will be having this a0. This a0 is 1 upon L, 0 to L, f of x dx, and we have an is equal to 2 upon L, 0 to L, f of x, and here this is going to be cos of n pi x by L dx. Now, what happens if I have the function f of x is an odd function in the interval minus L to L. Okay, so we can have the next, let f of x be an odd function defined in the interval minus L to L. Okay, so we have, this is an odd function, so that means a0 and an are 0. Okay, and what we get then, and the Fourier series expansion of f of x is given as f of x is equal to summation n running from 1 to infinity bn sine of n pi x by L. So this equation 1, where bn is equal to 1 upon, here you will be having, is going to be 2 upon L integral 0 to L f of x sine of n pi x by L dx. Okay, so this is how we are able to get the formulas depending on the interval as well as the function property, that whether it is going to be an even function or odd function.